Hi, folks. So last time we were talking about computer systems and we were talking about Boolean logic, and in particular, we were talking about Boolean simplification. So remember, we did an example where we had buttons B1 and B2, and we wanted to unlock a door. And so we showed that we could do sum of products or product of sums in order to write an Boolean algebra expression for the output, the lock, whether it was locked or unlocked, as a function of the input variables, the button presses. And then we showed that if we used a K-map, a Carnot map, that for a relatively complicated algebraic expression in terms of 4 buttons or even up to 6 buttons, we could combine adjacent terms to reduce the complexity. So now that we've got an idea of how we're going to write combinational logic, we want to talk about, well, how are we going to implement it? Because if we can write it, that's all well and good, but we should be able to do something with it. So the first thing that we're going to do is we're going to draw pseudocircuits. And so pseudocircuits are things you've probably seen before, where we have symbols to represent our combinational logic operators, our and, or, not, NAND, and NOR. These look kind of like circuit elements, and in fact, we're going to use similar things in circuits as well. But these are actually what we call pseudocircuits. So we can draw out a representation of logic, just like we draw out a circuit diagram, and we can use these standard symbols, and then we can take that from a pseudocircuit into an implementable circuit by adding some additional stuff. And what I'm going to show you is that implementable circuit may not actually be electric. But these are our pseudocircuit elements. And remember that we've got our NAND and our NOR operators, the not and not or operators, and these are really important. So we can say that NAND is going to be the not of the and of a bunch of inputs. As shown, it's only got 2, but you could get 3 or 4 or 6 inputs. And NOR is going to be the not of the or of these inputs. And so when we actually put together an integrated circuit, which we're not going to deal with integrated circuits in terms of building an integrated circuit in this class. We want to assemble collections of integrated circuits. But if we were going to design an integrated circuit, we would be focusing more on the NAND and the NOR, because remember, they're going to be lower part counts. They're going to be cheaper and easier to implement at the IC level based on the transistor structure. So if we wanted to convert everything to NAND and NOR logic, because it's cheaper to implement, because it'll be great for the inner workings of an IC based on the transistor structure, then we've got De Morgan's law, which helps us convert AND and OR logic to NAND and NOR. So on the left, you can see that I've got my, let's flip back here, I've got my, remember my NOR is going to be my pluses, my NAND is going to be my dots, my AND. So if I've got X or Y, I could make that the not of not X and not Y. Which is to say, if I've got my or, which is written in there, I'll write it in there. I thought it was an animation. If I've got my or in there, well, then I can take that and I can rewrite it as my NAND and a couple of nots. And so X and Y would be going in here. We not them both, we reverse them, so we get X not and Y not, and we NAND it. Which, alternatively, I could write that as a NOR with a not. So these are two different representations of the same thing, but it may be simpler to implement it at the transistor level. We can do the same thing with X and Y. We can split it into the not of not X or not Y, or we could then write it out at the bottom there with a NAND and a not. So those are some different ways that we can convert using De Morgan's law. Again, the whole point of this is that at the IC level, when you're designing the inner workings of an IC, this may be more appropriate for you. So What are we going to do? Well, we're actually just going to use IC chips. And in particular, in this class, we're not even going to use the IC chips as much because we know that we can do this whole thing in software as well. And I do want you to think about when is it valuable to implement in hardware versus software. When think about your project, is it going to be perhaps cheaper and easier to do it in hardware and then pull the result into software for operations? But if you want to do this sort of logical operations in hardware and you want to do it at the 0 to 5 volt level, TTL voltage levels, then we'll use the 7400 series ICs. This is a relatively old series. They're a standardized sort of thing, so you can get them from different manufacturers, and they have standardized part numbers. So for instance, a 7404 is going to be a collection of inverters. There are going to be several inverters in one single dual inline package, or surface mount, I suppose, but we're going to use the dual inline packages because it's convenient for your breadboards. And so there's going to be a standardized layout of the inverters. As you can see here, that's weird. I'm going to get my pen going here. This is a 7400, which is a NAND, and you can see that we've got 4 of them in there. It's a quad 2-input gate NAND. You definitely have to hook up the ground, you definitely have to hook up the power, and then we'll have, the first one, the second one, and then depending on your numbering scheme here, the third and the fourth. The third and fourth might be reversed depending on the pinouts that you're looking at. And so for the first one, it'll take inputs X and Y and give output Z. And so Z will be X and Y NANDed. And you've got 4 of them in this package. You can get similar sorts of 3-input gates. You can get 4-input gates, and it's just a standardized set of parts. It's called the 7400 logic series. So let's look at our door lock example. So if, for instance, we wrote it out as the lock is unlocked when we get B1 and not B2, then we could rewrite this as the not of not B1 or B2. And so we might write this out in pseudo circuit. There we go. We've got B1 and B2 as inputs, and we will run B1, we'll run B2 to our not, and we'll run B1 and not B2. So this is not B2 into our AND here, and then we'll get the output as a lock. Or if we convert it to NAND and NOR form, we might write it out this way. B1 and B2. We'll run B1 through our 7404, which, let me flip back real quick. 7404 is our hex 1 input inverter. So I'm going to use 1 out of the 6 that are in there. So that's my not B1, and then I will NAND those, I'll NOR those two to get the lock. And so that's an equivalent form. So these are, again, pseudo circuits. They're not ready for implementation. I mean, I do have part numbers listed in here, but you notice that this is a pseudo circuit in that it doesn't include the power, it doesn't include the ground, it doesn't include things like bypass capacitors. All it has is a single gate, and it just says, well, you could get this out of this package. It's a pseudo circuit. It's not ready for implementation. If we do want to implement it, and we're going to use the NOR variety here, well, I know that I can implement this with a 7404 and a 7402, and I've got my B1 and my B2 as inputs, and I've got power supplied to both of them, and I've got ground to both of them. And so that's my 7404, that's my 7402. So if you trace it through here, B1 is going to come into pin 1 of the 7404 and come out here, so this is going to be my B1 knotted. And so not B1 and B2, and what I'm going to get out is lock. Now, what's missing here is that we're also going to need our bypass capacitor. I'll draw that in. So this is just a capacitor between the power supply and ground, and I put it as close to the chip as possible. And, for that matter, I probably want to put one on each of them. And so what'll happen here is that when the chip is active, it may occasionally need a little more current, and so the bypass capacitor is storing energy, and when the chip needs a little more current, kind of like a fan on your external AC unit that needs a little kickstart, it'll draw it from the capacitor. So it's a quick way to get current, and so helps it helps supply the power to the chip. And so the bypass capacitors are very common. You typically put one per chip. You put it very close to the chip, and so it provides a little bit of a kick for that chip. So is this the only way to implement combinational logic, Boolean logic? Well, no. You can also do it using relays. You can also do it with fluids. You can use a PLC. We were just talking about TTL logic, but you could also have CMOS logic, which CMOS logic you can do with a 7400 series. There's particular designations for CMOS as well. Or you could pull all of your different signals into a microcontroller and run the whole thing in software. Now, there are advantages to each one of these and some disadvantages, and in lab you're going to explore some of the advantages to the 7400 series compared to doing things in software, but there are other times that you might want to use relay or fluidic logic. So what's relay logic? Well, it's derived from relays, where you've got a solenoid and a contact, and when you energize that solenoid, it's going to flip the switch, and the switch in this case is going to flip from this first output to this second output, so you're controlling the direction here. And so I might connect one of those to the rest of the logic, and so if there is no circuit formed, it's an open circuit. It'd be a 0. If it's a closed circuit, the switch is closed, it'd be a 1. And so because I can choose which of these to hook up to things, I can make the relay either normally open or normally closed, depending on whether it's energized. So if I put two relays in series, then you can see that they both have to be energized for there to be current flow across. And so that would be an AND. I need A and B to be energized in order to make the circuit. Compare that to putting two of them in parallel, when either one of them will allow it to go, and that'll be A or B. So is this going to still be used? Are you still going to see this in practice? Well, in large-scale logic, it's relatively expensive. It's relatively slow. You still have the arcing issues when these physical switches are moved. So you might see it replaced by solid-state logic, which we talked a little bit before about solid-state relays. You might still see it used for thermocouples and high power. You can also do some fluidic logic, which it's a relatively old technology, seen in the 60s. And I like this idea. You could use it in explosives or jet engines because it's just moving fluids around. How does it work? Well, you've got some fluid flows, you've got signal flows, and you've got larger flows, and the signal flows are going to redirect the larger flows. So let's look at this particular one. The fluid's coming in, and it's branching, and we've got this additional signal that we might add here, and if we add that signal, it's going to stop the flow through the rightmost branch. So we can affect the fluid by adding this additional smaller stream. So for instance, in a complicated arrangement like this, I might have jet A going from bottom to upper left. I might have jet B going from left to right. And so when I put them both in there, I get jet A and jet B going through upper right. So you can see that I can write some logic in the same way. It's just going to be based on where the fluid flows are going. Here's another one, an OR. If I put the power stream, this is not the control stream, but the power stream is going output 1, then if A or B enters, it's going to drive that stream to output 2 instead. So again, this is potentially useful if you've already got fluids, like in a jet engine, or if you're worried about electronics and power causing an explosion, like in an explosive. You want to not have anything that could potentially trigger the explosive earlier. Maybe you'd use your fluidic logic instead. So again, that's an and and or made entirely out of fluid flow. Another thing that you'll see is programmable logic controllers, or PLCs. We're not going to use them in this class, but they use the same logic idea as relays, what you might call a ladder logic. And so you're going to lay them out in the same sort of way that you've got symbols for relays that are normally open, symbols for relays that are normally closed. You can put them in parallel, you can put them in series as is shown, and you've got lights indicators to indicate that something has happened. It's a relatively well-known, easy-to-use sort of process. So here we go. Here's a PLC. It's got a switch on one side. It's got an indicator on the other. And so when the switch closes, the light comes on, and it's relatively simple. Internally, it's got the effect is one relay in there. So the switch is activated. The lamp comes on. So why might we choose to use this? Well, the ladder logic is relatively easy to understand, and so you don't have to be an expert in computers, you don't have to be an expert in engineering, you don't have to be an expert in electronics in order to program this, which means that it's well suited for use in factories or a place where you'd want multiple people to be able to make changes relatively simply. They're also ruggedized, which makes them nice for use in a... I'm sorry, my dog just walked in and made noise at me. It's ruggedized for use in a factory setting or anywhere else that you're going to be worried about shock or um, dust or any sort of contamination. So would you want to use this in another sort of setting? Well, it's completely reproducible by microcontrollers, so if you're not worried about the ruggedized nature of it, if you're not worried about the convenience for non-experts for programming, well, then maybe you just want a microcontroller instead. But it is still an option, and it's still something that's prevalent in industry. We could also go down to the diode level and make ourselves some passive logic circuits, and you'll do this in lab as well. So for instance, I've got two diodes and a resistor. My diodes here are going to be connected to my inputs X and Y. I've got VCC as my power there, and the output is going to be Z. So I think you can see here that when I have low on both X and Y, then that allows current to flow from VCC down to the node and then through both of the diodes. And so then Z will be pulled low. If either one of these is low, then current is flowing from VCC to X or Y, whichever is low. And if they're both high, then no current is flowing and Z must be high. So if you look at this is clearly a logical operator, and in fact, this is an AND operator. So we can make an AND operator with nothing but diodes and resistor. The problem with this is the cascade ability. You're not going to be able to do much with them. You're going to have to use amplification. If we want to do some resistors and transistors together, here's two transistors and three resistors. Now we've got X and Y in there. You can see X and Y are going to trigger the base of these BJTs. And so when the BJTs are triggered, then we're going to get current flow from VCC down to ground. And so there's our truth table again. So if these are both low, then neither one of the transistors is triggered, and we get a high. If either one of them is triggered, then current flows, and we get a low. And if both of them are triggered, then we get a low. And so you can see that this is actually a NOT or a NOR gate. So this is the inversion of our typical logic, and you can see that if this is relatively easy, then this sort of shows you why NANDs and NORs are popular. There's not a lot going on here. Relatively few components, which would make it easy to reproduce. However, it's relatively slow. It has relatively high power consumption, so there should be a better way to do this. And that's where we get into transistor logic. And transistor logic is what's happening on the inside of your 7400 series, well, some of your 7400 series chips. It's a lot of them now have been replaced by CMOS insides that simply behave the same way in terms of voltage limits as your TTL logic or transistor logic. So what's going on here that is particularly interesting is this spot right here, Q1. So Q1 is a multiple emitter transistor. This is a transistor that's got two emitters going. And so it's kind of like if we put in a resistor to a node and we had a diode going one way to what I'll call VB. Well, actually that's VB right there. And going the other way, we had diodes going to X and to Y. And if you think about the insides of your transistor, the PNP, well, sure enough, NPN, those are PN junctions in there. A PN junction is a diode, so this is a good way to do it. And so if you think about this right here, well, this looks really similar to that diode logic we were just looking at. So when X or Y is going to be low, then current can flow, and when current can flow, then you're going to see a voltage at VB that's going to change. Now it's got the diode in there, so it's slightly different, but it's the same idea as that diode logic and. So with that in mind, you can work your way through some of this logic. You'll also see that there's going to be this thing here that we might call our totem pole output stage. And that totem pole output stage is going to give you a low output resistance at high. So this is one particular 7400 chunk. And if you look through your logic here, if X and Y are both low, then the output is high. If either one of them is low, then the output is high. And if they're both high, then the output is low. What is that? Well, that is our, come on, animations. That is our NAND. So there's lots of variations on this. They all operate on 0 to 5 volts. And so they'll work nicely with your digital inputs on your microcontrollers or your digital outputs on your microcontrollers. And this is one of our more common packages. So in TTL, we can make our AND gate out of a NAND gate plus an inverter. So this is our NAND gate. This is our inverter. And you can see right away that if the AND is a NAND plus an inverter, then if we use De Morgan's law, then we can get rid of that inverter and we can save ourselves a transistor and a resistor. And so if we've saved ourselves a transistor and a resistor, well, that's saving components. And so that's why when we're doing larger ICs that are going to be based on the same sort of insides, that we would choose to use De Morgan's law and do everything in terms of NAND and NOR, because it uses less components. In this case, it's only one transistor and one resistor, but that's still saving you some money. Also interesting, in this particular one, let me get rid of my squiggles here. In this particular one, this is an open collector output. Open collector. And we talked about open collector a little bit before. What are your variants for TTL? Well, you're going to see 74s, 7400, 74L00, 74H00, 74S00, 74LS, 74AS, 74ALS. What do they all mean? Well, your 7400 by itself is going to be your standard. That's the original. That's what things are based off of. There's a low power. There's a high speed. There's a low power Schottky. There's an advanced Schottky. Whoops, I skipped a couple there. The low power Schottky is the LS, the advanced Schottky is the AS, and the advanced low power Schottky is the ALS. So as you go through these, let's see here. So in terms of the power consumption, you can see that the low power uses only 1 milliwatt per gate. The low power Schottky uses only 2. Compare that to the advanced Schottky using 20. So it's substantially lower power. What about the propagation delay? Well, the propagation delay, remember, is the time that it takes between when you send something into it and when you get an answer out. And so if that's relatively small, then this is going to have a lower impact on your combinational logic. Now, don't forget that your sequential logic is going to be different. But let's look at these propagation delays. Your advanced Schottky, 1.6 nanoseconds, compared to your low power without any other stuff, 33 nanoseconds. So the propagation delay is going to vary quite wildly as well. There's also your voltage limits here. We're going to talk about these a little bit later. So just for a point of comparison, if you were looking at 7404s, I looked up some prices a couple years ago on DigiKey. They haven't changed that much, so I'll give you just kind of a ballpark idea. For a 74S, it was 48 cents a piece. For an LS, it was 22 cents a piece. For an AS, it was 41 cents a piece. And for an ALS, it was 26 cents a piece. So we're not talking particularly expensive per component. But again, these are about double from the cheapest to the most expensive. You need to choose the one that's appropriate for your particular application. As I mentioned before, CMOS is another option. CMOS is built on your MOSFET or your FET transistors. Remember, TTL was built on your BJT, your bipolar junction transistors. And so we worked through in a previous lecture how to make a simple inverter. Well, here is a simple NAND. So in this case, you can see I've got 2 transistors here, 2 transistors up here. If A and B are both low, then Q1 is off, Q3 is off because those are both powered by A and B, and then Q2 and Q4 are powered by not A and not B, so those are both on and the output is high. And you can work through the rest of these. Why are these good? Well, they use relatively low power. They've got a similar voltage range to TTL, so you can interface them, and they are very sensitive to static electricity. Remember, the power used in these is going to be in the switching, not when they're sitting there at idle. If you want to interface CMOS and TTL logic, you need to make you got to make sure that you've got the right variants hooked up. So let's look at your CMOS variants. Notice again, these are 7400 series, but these are 7400 series variants that use CMOS internals. So you've got your high-speed CMOS, your high-speed CMOS that's compatible with TTL, and your advanced. So notice the propagation delays. Propagation delays, the lowest here is 4.75 compared to nanoseconds, compared to a 1.6 nanosecond on the fastest of the TTL. So the TTL might be faster, but look at that power dissipation. So for the idle power dissipation, 0.0025 milliwatts, that's tiny. That's almost nothing. Let's see, the total power dissipation per gate, remember it fluctuates as a function of frequency. So if you're doing relatively low frequency stuff, then you're still pretty close to the idle, which is not a big deal. And that's the real advantage here of the CMOS, is the power. Again, we'll talk about the voltages later. So that's what I've got for you. With that, you should be able to implement some TTL and some CMOS logic, and you should at least be able to say that you've heard of relay and fluidic logic. You should be able to draw some very simple pseudo-circuit representations of logic and then convert them into a circuit diagram for implementation or into software for implementation. And so our final video that I will record shortly here is going to be about practical considerations of putting together 7400 series logic, what to worry about when you are actually building a circuit.